There. Okay, so I didn't want to make a video right now. I got stuff to do, but I was doing a little research right before I was heading out, and I saw this video clip of the Ellen DeGeneres show about centripetal force. So check this out. This is what they're teaching kids. Now, it may seem kind of a fine line as to what's I can't have that. That is loud as hell. Okay. Moving right along. Still working here. There we go. That ought to be better. Turn that down a little bit on the old tube amp. And go.
Take a look at this. You're just going to use a clear balloon. So you're going to go to the store and you're just going to buy a clear balloon.
Okay.
And in that clear balloon, you're going to put a penny. So I already put one together for you. So this one will be yours.
Okay.
So the penny goes into the balloon like this, and now you blow it up. So remember when you went to the circus as a kid, that guy in the motorcycle?
Yeah.
And he would go in that cage and kind of go round and round. Centripetal force, not centrifugal, but centripetal.
Centripetal.
So watch this. You're going to hang on to it and shake it up a little bit and then spin. And as you spin like this, you get this beautiful spinning penny sitting inside. Isn't that just gorgeous?
Oh, that's so cool.
It just goes
I think I didn't
around
do
and
mine
around
fast
and
enough.
around. It's kind of like those planets going around that sun and the moon going around the Earth. That satellite that's in geosynchronous orbit that's sitting there just around and around and around. And now notice that if we were doing this on the space shuttle, the difference between what the kids would see down here in the space shuttle is that up in space that would just keep going and going and going. But of course the effects of gravity continue to pull it down. Now this is a nice quiet activity, and most teachers like a quiet activity at the end of the year, but you don't. So here's what I want you to do. This is the perfect thing. This is a hex nut. So you find a hex nut and you drop it down inside here. Imagine a room. I just came back from El Centro, California.
Yeah.
In a room of 100 teachers all doing this at the same time. Spin that one and listen to that one.
Oh, my finger got it.
This is a screaming penny, which is just beautiful. So now we get vibration. This is a librarian's worst nightmare, all right? Hey kids, let's go and examine science a little bit. Is that fun? Centripetal force. But you know the one that everybody wants to see you do, of course, is this. And so here is the device that, of course, you're just going to want to make it home. Because why would you want a spoon?
Now we'll get to this in just a second here. Centripetal force is said to be the force you feel mistakenly pulling outward because of moving in a curved path and changing direction. Now if I search this, what I'm going to come up with is it's going to tell me that centripetal force is, sorry about the extra noise there, centripetal force is the resistance to changing direction, because a mass, a body, a motion will continue to stay in motion unless acted upon by another force. So the change of direction, like if you were in a vehicle and the vehicle makes a sharp left, you're going to hit the outside wall to the right because your body wants to keep going straight, but the car's starting to curve, which is understandable, makes perfect sense. But the claim is that centripetal force is what keeps the object in a curved path. If you're spinning something on a string, they say it's the string that the centripetal force acts down the string. And the centripetal force keeps you in the curved path. That's not the string being tethered. Or same thing that's what their claim is, that it's just the change of direction that keeps the curved path. But the curved path only comes into play because of the changing direction. It's a little Jedi mind trick to support gravity, of course.
you're gonna stir up your liquid.
Right.
You need this tray, all right?
Of
So
course.
the tray goes like this. Is that kind of nice? And now to that tray, we put a glass of water, which is nice. So a little glass of water goes here. And you could just do one, but you are going to have a dinner party, so we need to have a lot of these, all right? So here we go.
Oh, I
A little
love the dinner
centripetal force,
parties.
we would only hope that it would just stay in place, okay? So I think you're going to be just fine. And if not, gosh, was it fun seeing a meteorologist spin this over
And I'm
her
wearing
head.
white today. I'm so
Okay, you're gonna
glad
be
I
great.
heard about
All right,
this
you're feeling
experiment
good?
before.
All right, good. So
Feel
now
good.
here's what I want you to do.
Yeah.
You're gonna get a little just kind of rocking action. That centripetal force. It's a center-seeking force. Ready? Kind of up and over your head. One, two, three. Up and over your head. Here we go. Nice. See, you did it. You did it. Go again. Come on. Be brave. Be brave. Nice.
Here we go.
Nice. It's okay. It's okay.
Water just went everywhere.
$100,000 million cameras, but you're fine. At least the dinner party had
Centripetal force.
one left.
Where'd it go? Why did the cups go flying off? The centripetal force should have pulled all the water and the cups back to the middle. My gosh, I'm so confused. Okay. Yeah, alrighty then. Let's just see what one of their other ones are. This one's only 51 seconds. Oh, he's going to spend some stuff around here. Steve Spangler. Mr. C. Mr. C. Okay. What? Circular moon with hanging mass physics demo. Let's see what this guy's got going on. Straight out of India. Madhav Malhotra.
Hi guys, this is Madhav. I'm going to describe a quick experiment I'll show you that shows the effects of circular motion, and in particular shows how the speed at which a mass is spinning with
Let's see what you got going here.
speed went down, then the mass started falling down again. So what we saw just there was some force started to oppose the force of gravity, and when the rate of spinning here, when it got smaller, that opposing force also got smaller. I'll show you this one more time. You can see pretty stable height here.
Velocity. The velocity of the weight moving in the curved path connected to the string overcomes that of gravity and pulls it up. I still don't see a force going inward. Where's the centripetal force that moves towards the center if it's lifting the weight?
At the speed that I'm spinning at, pretty stable height. I'm going to stop applying force so that this starts spinning more and more slowly. And when that happens, now the mass starts to go down. Here's the last case. What happens when I am spinning at a very high speed?
The faster you go, the weaker the centripetal force, apparently.
You can already see that the mass, it started to go upwards. I'll try and make this a little bit more gradual. So right now, it's pretty stable. I'm going to apply more and more force. You can see, relative to my finger, the mass went up. I'm going to apply less force. Mass is coming down. I'm going to stabilize it here.
Centripetal force will tell us that centripetal force is what's making the weight at the top move in a curved path. It's not the string physically keeping it in a curved path. No, it's the centripetal force acting upon the string. Yeah, that's what is said. Come on now. Alright, you know, I have a presentation for centripetal force, but I don't know if I should try and go through it right now because it's going to take a little while and I have some stuff to do, so I'm going to just stop right here. Maybe I could show it real quick here. Let's see. What's in, this one. Somewhere. Is that to one. No, that's where I put the other stuff. Okay, so up there it would be stink. There it is. Okay. Centripetal. Now this was one of my first things that I came up with, just thinking about the subject for the level unmoving Earth. And it would be, not a proof of a level flat Earth necessarily of the flat Earth, but a disproof of a globe, I guess you'd say. One of the impossibilities. So I believed there was a thing called centrifugal force because I heard about it when I was a kid, but I guess it's not a real thing. It's just a made-up word for centripetal force that pulls inward like gravity, except not. So this was my premise, that since we all know, we all been on a merry-go-round, it only pulls you sideways. When you spin something, anything on that thing is going to want to slide outward. I think we all can establish that as a fact, even though centripetal force is said to be pulling it in. What they say is centripetal force what keeps it in a curved path. The fact that it's moving in a circle on something is what keeps it in a curved path. I can't stand the Jedi mind trick on that. It's just beyond me. So balancing this is what my premise here. Balancing anything straight up and down would be impossible except for at the equator, on a globe that spins due to the force vector between centrifugal and gravity. It's if you grant gravity on a ball. And centrifugal force is weakest towards the center because it's the smallest path, the shortest distance in its path. But as you move away, which is called increasing in radius, and I lost my mouse right now. Okay. When you increase the radius, it increases with it. And as farther you increase the radius outward, the more that force increases. Right? So centrifugal force, although weakest near poles, pulls sideways, unrestricted. There's nothing, counterbalancing it. So no matter how weak the centrifugal force would be calculated, nothing to oppose it, the water could not remain on the poles, because what's the force opposing this motion right here, away from the center line? Is anything opposing it? Gravity's pulling it at an angle, so it's not opposing it here. Right here it's at a 90-degree angle. So here it's at about a 45-degree angle. So if you built a building right here, it wouldn't point straight up out of the ground surface of the ball. It would have to split the difference between those two and go at an angle. Let's see if I can just do this. So, might as well finish here. On a globe, Happy New Year's. Every line of latitude has a different angle relative to the line of axis. As I was just going over right there. So. Next slide. On a globe, up is away from its center of mass and down is towards it. There is no level, as every point on the surface is subject to curvature. Here's my example. I think it's pretty self-explanatory looking at that. That would be correct, right? It also demonstrates how, if you were looking at a distance, you should see things pointing away from you. So, if you were standing here, and you're a great big person, and you were to look over to here, and this was some, big buildings, the buildings should be pointing away. But when we look across the great distances, things don't seem to point away. That's a side note from Centripetal. Oops, I think it double skipped in there. Now this is, the ancient Hebrews' conception of the universe. Waters above, waters below, and the earth was floating. And I'm pretty sure that implies that the tides have to do with the earth's surface kind of bobbing up and down at a steady rate. And not something moving, not that we're moving in gravity, because gravity is ridiculously stupid. And here's what I overlaid the double torus, because in my cosmological model, this is the the as above, so below shape of the universe and matter. If you go down to the atomic level, its energy structure, the thing that gives it its substance, the energy that holds it, the placeholder for substance, that holds the energetic states that we consider to be substances, solid things as we perceive them, I think has this shape. And it's a magnetic line of inertia. So, but I just overlaid this to kind of show how that kind of falls in line with that. And this is my cosmological model. I'm just throwing this in here. It doesn't necessarily have to do with the centripetal force, but here we are. We have a double torus. We've got the magnetic plane of inertia. We've got a high positive potential at the top and then high negative potential at the bottom. I swiped this torus shape from a website that was putting forth the galactic halo and galactic disk. So like they're saying that this shape right here is the galaxy, and that our planet is one of the little things, or our solar system is moving around like I have the sun or the moon moving around in this model. I think they have the right model, they're just at the wrong scale. It's right down to this scale, because this gives you the level round Earth. It gives you the positive and negative charge separation that we know exists because of atmospheric electricity, which gains it. I can't remember right off the top of my head right now, but as you move up, you have more and more potential. You know, in my cosmological model, lightning is a buildup from the ground of electrons. It basically makes an electron bridge towards this positive potential. Once the electron bridge is built high enough that this positive potential can overcome the gap, it strikes, creating a plasma that burns the atmosphere all the way down to the ground, and we see a lightning strike that goes to the ground. But the path to the ground is already laid out by the electron bridge. I'm going to have to make another video on that. Okay. So, here's my presentation. The Centripetal Farce. Because this came from Newton. Okay, so gravity theory states that a force exists between all bodies of mass, pulling towards each center. Earth's pull holding it together and us on its surface. As a sphere exhibits curvature at all points, there is no objective level. Up and down are equal to, towards or away from its center of mass. So I'm saying, so there you go. We're all familiar with the basics of Newton's gravitational theory. However, Newton himself knew that centrifugal force produced by rotation, or moving in a curved path, a force well known to all, opposed his theory as gravity was the weak force and fixed, while centrifugal force increases with radius from axis. The bigger the circle it moves in, the more force it has, pulling outward, not inward. Newton knew that gravity, because of its fixed nature, I'm sure, couldn't stand alone, but as the world's preeminent scientist and head of the Royal Society, he was in a position to rewrite physics. Seizing upon an idea first proposed by Huygens, he added another force to physics to support his gravity theory and named it centripetal force. It was coined by Newton and discovered. A force that he said pulled inward on mass, moving on a curved path, and that the apparent outward pull of centrifugal force was due to resistance of a mass in motion, its resistance to change in direction, and that centrifugal force was not real. See, there's a fundamental difference between moving in a curved path like that and being a solid object rotating that has its outer edges traveling in the same, trajectory as a curved path. It is a curved path, but it's a solid object rotating and has a transition from its outside to its inside of speed. I mean, it's fundamentally different motion. So anyway, now with centripetal force, it's the force is centripetal is the mass times velocity squared over radius. An inward pulling force. That's what he named it. he had the extra energy needed to balance his gravity calculations. However, like gravity, centripetal's inward pull can't be felt. We feel an outward pull, but only from resistance to changing direction from moving along a curved path. And that's what I'm saying the claim is. They claim that the centripetal force is what keeps an object moving in a curved path. Just think about that part. And my question, is centripetal force the cause or the effect of moving in a curved path? And how is a rotating mass and a body in motion on a curved path subject to the same force when fundamentally different motions? There's my claim. Centripetal can't keep it, a moving body in a curved path when it arises from a body moving in a curved path. They're trying to say it's the cause of the thing that it arises from. Oops, wrong there. Move along. And so this is some clips from my other video where I had a conversation with AI co-pilot about centripetal force when I first heard about it here recently. Anyway, so I asked to tell me about it. And it says centripetal force is the real force that keeps you moving in a circle, pulling you towards the center. It's what actually counteracts that outward feeling of centrifugal force experience. Quite the duo, so what sparked this curiosity? It asks me. And I show me some examples of centripetal force. If you ever spun the bucket of water without the water spilling, that's centripetal force at work keeping the water inside. Or if you've seen a car take a sharp turn and everyone leans in, that's centripetal force pulling them inward. Pretty nifty, right? No. Stop, hold it. What happened? If you're in a car and it takes a sharp turn, are you pulled in? Like, the car turns this way, do you go in the way the car is turning? Or do you get pulled out, away from the direction that the car is turning? It seems that AI does not understand the basics of force and direction and motion. Is this the Jedi mind trick right here? They're just saying something that's patently opposite of our experience and saying its effect. And then I said, are you sure it's not the tires that keep it in moving along the curve? And there's the answer, sort of. The tires grip the road, centripetal force is what keeps the car from flying off the curve. It's not the friction of the tires and the weight of the car pushing down on the road that keeps it from flying off. It's the centripetal force pulling inward that keeps the car from flying off the road. What? So the tires help provide that force by keeping the car on the road. Fascinating, right? And here's what I said, keeping it on the road. I thought that would be gravity, right? Because that'd be what keeps the car on the road. A centripetal force is what keeps an object moving in a curved path, like the gravitational pull keeping the moon in orbit around the Earth. It always acts towards the center of circle of the object. They haven't given any even slightly logical suggestion as to why that would be the case, that there is a force that moves towards the center at all, not gravity or centripetal. Then they say you could try the object on a string, the feeling of the object pulling away as you spin it is the centripetal force acting on it. Give it a whirl. Picture this, you're holding the string with the ball attached, swinging it in circles over your head. Feel the ball is hugging outward? Sure, yeah, it's trying to pull my hand that way. That's centripetal force working to keep the ball moving in a circle. No, that's the force of my hand holding the string that's keeping the ball moving in a circle. Hello! Does this experiment make it clearer? It doesn't. And I said, seems like it's not real. A co-pilot says, it may seem like that, but centripetal force is very much a real concept. Notice it says it's a real concept in physics. It doesn't say it's a real thing. It says it's a real concept in physics, which I agree. It is a real concept. An erroneous concept, but it is one. Without it, objects wouldn't follow curved paths, like the ball and the string. Centripetal force keeps it moving in a circle by pulling it inward. It's not some physics fairy tale. So when you're spinning a ball on a string, it's not you holding the string and the string being solid connected to the ball that keeps it in a curved path. It's centripetal force which arises and acts, which is invoked to keep it on the curved path, and then the string keeps it there. The string's just how long for the ride, and your hand just happens to be there. I mean, what are they trying to say? Their premise makes no sense, and it's from Newton. Okay, so Newton's full of shit. And here's what the definition of centrifugal force is, as when I asked it, because it's not a thing, but there's a definition for it. Centrifugal force is the apparent force that seems to push an object outward when it's moving in a circular path. However, it's not the real force acting on the object, it's actually the result of the inertia of the object, which wants to move in a straight line as per Newton's laws of force and motion, which, by the way, disproves the solar system model by his very own laws of force and motion. That's a different piece too. Let's just finish this up because I gotta go do some stuff here. I gotta change the tire. Imagine you're spinning the ball in a string while you're holding the string, swinging the ball outwards, moving in a straight line. Inertia. While the string provides the centripetal force needed to keep it moving in a circle. So strings provide centripetal force. What if there's no string, such as in the case of, an orbit? So centrifugal force is more about how we perceive the motion rather than an actual force acting on the object. Does that clean things up a bit? I think this is my last picture there. Okay. No, that doesn't clear things up at all, Copilot. That does absolutely nothing. Okay, so how ridiculous is that crap, huh? Did I get this one? I'm putting it out. Newton made up his centripetal force so that he could bolster his lacking gravitational theory, because without some other supposed force, this Fc equals mv2 over r, his gravity couldn't overcome what we all know to exist. That's the outward pull. And so, since he was the head honcho, right, the preeminent scientist and the head of the Royal Academy, or Royal Society, he just said, oh, it's centrifugal, I've discovered a new force. Look at my genius. I don't doubt that this equation here does measure something. It measures the centrifugal force. I mean, that seems like a valid equation, but it's not. Measuring and pull inward, there's no evidence that there's a pull inward whatsoever. You let go of it, they might say, you let go of the string, the ball will go tangential, meaning it will start to go in a straight line away from its curved direction. That still does not show an inward force. That shows an outward pulling force that when the tension is released, moves in a straight line. That does support it. It fits in line with Newton's force and motion, but it in no way is evidence of an inward pulling force. I have not seen a legit one yet. So I had a video on here, but I don't know where that's at. I'm gonna have to put that in my follow-up. So there's what we got. Signing off. Thanks for watching if you watched, and yeah, I mean, if you can understand how the centrifugal is not real and that there's a force pulling inward. AI just told us when you're in a car using the that curve, you notice that force pulling you inward? I'm like, no, I don't. It's not there. It pulls you outward. I think we all know.